Okay, Advanced Data. Good morning. This is your lesson for Monday, the 22nd of February. I know it's a bit late this morning or today. Just get time to try and get all these things done. So we're going to move on from what we were talking about last week and or a couple of weeks ago, because I had a wee break last week for new content. We're going to look at the interference. We did a bit of interference at higher, but we're going to take it a step further in advanced higher. And the first time we're going to look at is something called division of amplitude. Now, a couple of terms we're going to be using I need to explain to you and how they work before we can go on and look at the formulas and what the theory is. The first one is talking about phase and coherence. So we talked a little bit, again, we would have said something about this at higher, but just recapping this. So when the crests and troughs of two or more waves are aligned with each other, these waves are referred to as completely in phase. So when they're lined up and the crests and the troughs meet and the peaks meet and they move up, they go through their cycle at the same time, then they are known as completely in phase waves. When they're not aligned, they are always referred to as out of phase. And the amount they are out of phase can be measured by the phase difference formula. Now, the phase difference formula is this formula up here. We talked about that before when we talked about phase difference. When two or more waves are aligned so that the crest of one wave meets the trough of another, they are referred to as completely out of phase. So we have in phase, out of phase, and completely out of phase. Two or more waves can be referred to as coherent if they have the same frequency, the same wavelength, and the same velocity. They don't need to have the same amplitude, and coherent waves have a constant phase difference. So if something is in phase, then the crests and troughs meet. If something's out of phase, they don't meet. If something's completely out of phase, then the peak of one meets the trough of the other. And a wave is coherent if it is have a constant phase difference. What it means is that if you were to put the two waves together, they would be in phase with one another, but you shift them slightly and they're going up and down at separate parts. So they have a constant phase difference, which means they're always separated by the same amount on the waves. So a coherent wave doesn't have to be in phase, it just has to be two waves that are constantly out of alignment by the same amount, or completely in alignment if you wanted to, but they're not changing compared to one another. So the same wavelength, same frequency, and same velocity, but not necessarily the same amplitude. And we'll look at that higher, didn't you? So the phase difference formula is phase difference equals x over lambda equals 2 pi times 2 pi. So your phase difference is 2 pi x over lambda, and x is your horizontal displacement between the 2 points. Right, interference, this is just a bit of a recap of interference from higher with extra formulas and extra symbols in here. So when any two or more waves come together, this causes interference and interference patterns. So we're going to talk about what we learned at higher and build on that a little bit. In most cases, the resultant wave is the addition of the combining waves, positive and negative values about the central axis taken into account. So you've got a wave that's positive above the axis and a wave that's negative above the axis. These two values will add together, will combine and give you an overall waveform. Special cases when two coherent waves come together to produce interference patterns. So if two waves are coherent with one another, then they can line up and do some pretty important things, but they have to be coherent. So if two waves come together that are coherent in phase with one another, they double their amplitude. If two waves come together that are completely out of phase, coherent waves come together out of phase, they cancel each other out. Now, if the amplitude of each wave is the same, then that doubles it. If the amplitude of each wave here is the same, then they totally cancel each other out. This is known as constructive interference. This is known as destructive interference. So constructive interference waves meet in phase. The horizontal separation is 0, or it is one wavelength of difference, and the phase difference is 0 or 2 pi, as in one full wavelength. Destructive interference are completely out of phase. X is equal to half lambda, so the top horizontal separation between the two waves is half a wavelength, and the phase separation is pi, which is, you should know, half a cycle, which is pi. Right, reflections. We're going to talk about reflections. So when a wave reflects, there can be a phase change, and depending on the boundary of the two mediums. So these are two different boundaries. We're saying here that n, the refractive index of this substance here, has a greater refractive index, meaning it is higher density. If this medium here has a lower refractive index, meaning lower density. So this low density refers to this diagram, high density refers to this diagram. So low density to high density boundary, so the wave comes in and when it bounces back, it actually comes back and it's out of phase by half a wavelength. What you'll notice there is that as it comes in, it comes back off at the same point, no, it actually comes back off and it flips. So it goes in and back out, and you'll notice there that this wave compared to this wave, there is half a wavelength difference. So there is a phase change of pi, a phase change of half a wavelength. This one here, when it goes in, it comes back, there is no phase change and there is no difference in wavelength. So this one here coming in and out, this is for a low density to high density, and this one here is from a high density to a low density. So bear that in mind. Low to high, you could have air to glass. High to low, you could have glass to air. So just bear that in mind. If it's going air to glass, it will have a phase change. If it's glass to air, there will be no phase change. Okay, the next thing to consider is something known as optical path difference, or OPD that we call it. So the velocity and wavelength of a wave changes as it passes through different mediums. So think about this as a normal wave passing forward. If you pass that wave through a higher density medium, then the wavelength changes, so the waves bunch up and there is more waves inside the high density medium. So through a more dense material, greater refractive index, the wave will have a smaller velocity and wavelength. So the wavelength shortens inside the higher density material, resulting in more waves for the same geometric length. So here is your geometric length, L. There are more waves inside here than there is if it wasn't going through the medium. The optical path length is the length travelled through the medium, this one here, calculated by the product of the geometric length L and the refractive index, so Ln. The optical path difference is the difference between the geometric length L and the optical path length NL. So the difference between the two of them gives us what's known as optical path difference. Now I'm going to go in and show you what that formula looks like in a minute once we look at some examples. Okay, we're going to look at the principles of division of amplitude now. This is a kind of standard example we're going to talk through, and then we're going to look at 3 specific examples and how they can be used. So this is to help you understand what the diagrams look like and how to make sense of them all. So I've numbered all these rays and then we'll talk about how they work at the bottom. So number 1 is the ray coming in. This is the light coming in to the whole thing. So the light comes in from air into a higher density material, usually glass. So light comes in. And what happens at that boundary where the dot is that some of it is going to reflect, some of it is going to refract. If it reflects, then it's an air-glass boundary, low density to high density. So number 2 has a phase change. Reflected ray from air-glass boundary, phase change is pi, equivalent to a half wavelength. So there's a phase change here. From there, reflecting back, there's now a phase change for 2. 3 is your refracted ray, air into glass. This optical path length here is n times the length. So n being n for glass, refractive index, times the length that's inside the glass. Number 4, some of it reflects at that boundary here, so we get total internal reflection here. And the optical path length of 4 is NL again because it's inside the medium. But there's no phase change at this boundary here because it's glass to glass, it's high density to low density, no phase change inside. Number 5 is the transmitted ray that goes through, and in all honesty we're not actually interested in that one. Number 6 is refracted ray glass into air, so once number 4 reflects back, this refracts again as it comes into air. So what we're interested in here is we're not actually interested in 5 at all, we're interested in these two. These 2 rays that are reflected back, one is reflected from here, one is reflected from here, and you come back, and when you're looking, or when the light comes in, you get this other waveforms coming off, 2 and 6, and it's 2 and 6 we're interested in. And we're interested in how 2 and 6 interfere with one another. So the optical path difference between 2 and 6 is the optical path length 3 plus optical path length 4 plus any phase change that we had there because of between the two of them. So this one here comes in, it reflects, you've got a phase change, optical path length here, optical path length here, and then you've got a phase change because of that one there. So this here, phase change here to come back, no phase change here, no phase change here, no phase change here. So this extra phase change is because this has got a phase change because it reflected. So the overall difference between 2 and 6 is the overall optical path difference between 2 and 6 is the difference between these two. It's this plus the phase change caused by 2. You put them all together and you get 2nl plus a half weight lambda, where 2 and 6 interfere with one another and may cause interference patterns. This is referred to as interference by division of amplitude, because the amplitude of the instant ray, which is 1, is divided into the reflected and transmitted rays, which go on to cause interference. This is the definition of division of amplitude, and this is how we use it. So we're interested in how can we use the interference of 2 and 6 to work anything out for us, or do anything for us. So the first example of this is known as oil films. Sometimes you'll see this in a petrol station where petrol has been left sitting on top of a puddle, and you get a rainbow effect appearing on the top of the puddle. So the light is coming in, it's reflecting and inside the puddle and the film, and it's coming back up, and you see it as a rainbow effect interference pattern. It's known as it interferes all different waves. The refractive index of the air is a 1, which is less than that of the oil film or the petrol film, which is more than that of the water. So the oil is the most dense of the three materials. So the air is a 1, oil is more dense, and the water is less dense than the oil. Interference between the two reflected rays is the same as the previous example. So these two rays, it's just the whole diagram just being spun on its side. These two rays interfere with one another, and you end up with an interference pattern caused by. Now they don't look as if they're going to interfere, they don't look as if they're parallel, but your eye takes these two rays and brings them together to a point, and they can see as an interference pattern on your eye. So the optical path difference, just like before, is 2n of the oil times d plus lambda over 2. This is in the last slide, the whole theory of that, if you just check the last slide. Now that's your path difference, optical path difference. Now for destructive interference we know that path difference equals m plus a half lambda, m being the order of minima for destructive interference. This is in textbook, if you want to go and check that up, I'll give you the pages in the assignment. So optical path difference is m plus a half lambda, where m is 1, 2, 3, etc., which is the order of minima. So you just take this formula up here, plug it in, 2n for the oil d plus lambda over 2 equals m plus a half lambda. Rearrange, you get 2n for the oil d equals m lambda. That's for destructive interference. For constructive interference, optical path difference equals 2nd plus a half lambda, just like you have up there, and that equals m lambda, where m is 1, 2, 3, etc. So that is for oil films. That's one example you'll see in the tutorials and in past paper questions. The second example is something called a bloomed lens. This is quite a common one to discuss, and it's quite a common application. Basically we use this to minimise reflections. So what we're trying to do is, what you often get is you get reflections on glasses, for example. So let's take my own glasses. What you don't want in a set of glasses is images to reflect inside the lenses. So when you look at somebody with glasses, the last thing you want to see is the images of the objects around about reflecting back, and you can't see their eyes. So you want to see their eyes, that's the whole point. You're also wanting to try and maximise the amount of light that comes through. So if the light is coming to me, to my glasses, I want all that light, all the amplitude of that light to come into my eyes so I get a fuller image. What I don't want is any of that light to reflect back and then I don't see it, because it's taken away from the amplitude of the light coming in. So two aspects to it. The non-reflective coatings and lenses, which this is, are to stop the reflections, so for others around about you so you can see your eyes, but also to maximise the amount of light that's going in and stop any of that amplitude getting reflected back and not being taken in by the eye. So destructive interference is resulting in no reflection and more light transmitted through the lens. So what we want to do is we want to take these two waves coming back and cancel them out, so there's no light transmitted, so no reflection and more light transmitted to the lens. We want to cancel these two waves out, and it's improving the image transmitted, improves the image that comes through to the other side. So the air to the coating, so this is a slightly different thing here, is the air's got a 1. The coating is something between the density of the air and the glass, and it's very, very, very thin, and it has to be, the density has to be less than that of the glass, and the refractive index less than that of the glass. So the air to the coating boundary, so this boundary here, there is an optical, there's a path difference of lambda because it's a reflected ray from less dense to more dense, and again there's another path difference here from less dense to more dense as it hits that coating glass boundary. So that's what these two are here. Therefore, there is actually no optical path difference between for the reflected rays for these two rays back. In the previous example, then there was an optical path difference here, but not for this one. But in this one, they both got it, so there's no difference between them. So for destructive interference, you're not really interested that much in the constructive interference aspects of it. You want to cancel these out. So we're interested in the destructive interference of these two. So the optical path difference equals 2n coating d. Notice there's no path difference formula part there. Equals m plus a half lambda, and m equals 0 because the coating is so thin. So we're making this m value 0 because because this coating is so thin, it's not got enough space to create more than just one interference pattern or one maxima. So the m comes out and you get d equals lambda over 4n for the coating, and that's the formula for bloomed lenses are called. Bloomed lenses are just coatings on lenses. You get this in cameras as well, and glasses, telescopes, lots of things like that. And it improves the light transmitted through. Right, the last example is something known as thin wedge interference, or divisional amplitude by a thin wedge. Now this is used, what we have here is two glass plates, one on top of the other, usually something like a microscope slide, these tiny little glass plates, and one very thin separation at the end, and this separation is something like a sheet of paper or a strand of hair, something that you can't really measure. But in a classroom, you could measure it in a lab with some fancy measurement device. In a classroom, you can't do that. So we'd use something like thin wedge interference patterns to measure this separation at the end of these two plates. So the light is incident onto this wedge, creates an interference pattern. These two waves here create an interference pattern. This interference pattern can be used to calculate the size of the thin separation here. Now there's 3 slides in this. I'm going to go through each one, and we'll get to the how we do that at the end. So the glass to air boundary, which is this one, glass to air boundary delta, the path difference is 0 and there's no change. We're actually not interested in the glass to air boundary, which in fact we are, because it comes straight through. There is a bit of reflected ray here, but we're not actually interested in that at the moment because it's such a tiny little wedge. We're interested in this glass to air boundary down here, which has no change in the path difference. And the air to glass boundary, which is this one here, there is a phase change of pi as we go back that way. So therefore the optical path difference is 2n air and t. So we've got 2 times the refractive index of the air times t. So it's really just this wee bit here we're interested in. It's these two waves coming off. It's lambda over 2, and it's 2t plus lambda over 2. Okay, so it's just for this little bit in here as it's happening. This doesn't reflect back because the angle is not sufficient enough to cause total internal reflection, but is here. Okay, I'll go into that in more detail now. So what we're looking at here is for this destructive interference again we're interested in looking at. I'll explain that in a second why we use destructive interference. So the optical path difference is m plus a half lambda, 2t is lambda over 2, m plus a half lambda. Plug that in, then you've got this triangle here, so t over x, so this little small separation t over the x is proportional to d over L, in fact it would be the same ratio between the two, therefore t is xd over L, plug that in and you get x is m lambda L over 2d. So x is just this distance from the end to a point, somewhere wherever the light is coming off. So now interested in this point. This is the point, the distance of point of minima from point of wedge. Now, when we talked about the destructive interference point, so we are saying the point from the end of the wedge to a destructive interference point. Now, this is what it would look like on top. You would have this kind of interference pattern, and you notice all these lines, and these lines represent, it's not that hard, not easy to see the constructive interference points, but the destructive interference points are seen as black lines. So the darker lines in the diagram above, or the darker lines in the diagram below, that's what we're measuring to. The end of the wedge to a dark line is given x is m lambda L over 2d. So x m lambda L over 2d is distance to any point, any destructive point, and the distance to the next point is basically just m plus 1, that, because it's the next minima along. So delta x, which is the distance between two minimas, two black lines, is the x dash minus x. Two formulas plugged in, do the subtraction, simplify down, and the difference between two lines is lambda L over 2d, and d is your separation. L is the length of the plates, d is the separation, and delta x is the spacing between two of these black lines. And that allows you to get the size of whatever object you're looking for, which would be d. And that's for thin wedge interference patterns. So there's your 3 examples for this. You'll find them all in your tutorials. You're going to attempt the 2 tutorials just now, and then obviously there's a Teams call as well on Thursday, and you can ask me any questions. This is quite complicated. It might take a bit of time. I think what we'll do is we'll see how you get on with it. I'm happy to give you as much time as you need to try and get the 2 tutorials done. There will be a check test as well, as usual, and I'm thinking that I might give you this week and next week to do it, but I'll speak to you on Thursday and see how we're getting on. Right, thanks.